May 19th, 43. Imperial Japanese Navy Technical Research Institute, Yokosuka Naval Arsenal. The metal crate sat on the examination table like a coffin containing the corpse of Japanese naval supremacy. Inside, carefully packed in American sawdust, lay a device that would shatter 2,000 years of warrior tradition with the cold precision of electromagnetic waves. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Captain Yoji Watanabe had been summoned from his post as technical liaison to the combined fleet, specifically to examine this prize. The Americans called it SC radar, ship control radar, a compact unit salvaged from a destroyer sunk during the Solomon Islands campaign. Japanese divers had recovered it from 40 meters of water, still intact in its waterproof housing. The crate had traveled under armed guard from Rabaul to Tokyo, its contents classified above top secret. Admiral Isoroku Yamamoto himself had ordered the analysis before his death the previous month. Now Watanabe stood before it with 6 of Japan's finest electrical engineers, about to open a window into a future where Japan had no place. The room fell silent as Watanabe's assistant used bolt cutters on the metal bands securing the crate. The wood creaked as they pried it open. Inside, wrapped in rubberized canvas, was a metal box roughly 60 centimeters square, festooned with cables, vacuum tubes, and components that seemed almost casual in their construction. This was not the handcrafted precision of Japanese electronics. This was something else entirely: mass production, standardization, American industrial thinking made manifest in circuits and cathodes. Watanabe had spent 3 years in California before the war, ostensibly studying electrical engineering at Stanford University, actually gathering intelligence on American radar development. He had toured the laboratories at MIT, visited the Radio Corporation of America facilities in New Jersey, observed the casual innovation that characterized American technical culture. While Japanese engineers labored for months perfecting single prototypes, Americans built dozens of variants, tested them to destruction, and moved on. While Japan's best minds worked in isolation, competing for resources and recognition, American researchers shared data freely, publishing findings that would have been classified secrets in Tokyo. The device before him embodied this fundamental difference in philosophy. Lieutenant Commander Hideaki Nakajima, Japan's leading expert on centimetric radar, approached the American unit with something approaching reverence. He had been working on similar technology for 4 years, achieving results that had earned him commendations and promotions. His laboratory at Yokosuka represented the pinnacle of Japanese radar research. His team of 30 engineers had produced working prototypes that performed adequately in controlled conditions. Looking at the American device, compact and robust, clearly designed for the chaos of combat rather than the sterility of laboratories, Nakajima felt the first cold touch of technological obsolescence. The examination began with external assessment. The American radar was smaller than Japanese equivalents by half, yet preliminary measurements suggested greater power output. The construction used standardized components, each marked with part numbers and specifications. Vacuum tubes were socketed for easy replacement rather than permanently soldered. Cables used color-coded insulation and labeled connectors. Every design choice prioritized maintenance and repair in field conditions. Japanese radar sets, by contrast, required specialized technicians and hours of careful adjustment. They were scientific instruments pressed into military service. The American device was a weapon, pure and simple. Watanabe ordered the unit disassembled with surgical care. Each component was photographed, measured, and catalogued. The process took 6 hours. What they discovered was not a revelation of unknown technology, but something far more disturbing. The Americans had achieved nothing. Japan's engineers didn't understand theoretically. The shock came from how they had implemented it. Where Japanese designs required hand-wound coils and individually calibrated circuits, the American radar used mass-produced components with generous tolerances. Where Japanese sets needed constant adjustment, the American design was self-stabilizing. Where Japanese radar required highly trained operators, the American unit could be operated by sailors with minimal instruction. The magnetron, the heart of any centimetric radar, told the most damning story. Japanese magnetrons were crafted by master technicians, each unit unique, requiring days to produce and weeks to perfect. Production rates averaged 5 units per month from Japan's primary laboratory. The American magnetron in the SC radar showed clear signs of mass production. Tool marks indicated automated machining. The cathode assembly used standardized parts. Most troubling of all, penciled on the magnetron's base was a date code and production number that suggested this specific unit was the 7341st, produced in a single month at a single facility. Nakajima did the mathematics with shaking hands. If this date code was accurate, and if this represented just one American factory, the production disparity was not measured in percentages but in orders of magnitude. Japan's entire radar program, encompassing every laboratory and production facility, might produce 200 magnetrons annually. The Americans were producing tens of thousands from individual factories. The implications cascaded through his understanding like a tsunami through a coastal village. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The technical specifications, once fully documented, confirmed every fear. The American radar operated at 10 centimeters wavelength, exactly the frequency Japanese research had identified as optimal for naval fire control. It achieved this with a power output of 75 kilowatts, double what Japanese sets managed. The receiver sensitivity exceeded Japanese capabilities by a factor of 3. Most devastatingly, the entire unit could be manufactured, tested, and installed on a ship in less than a week. Japanese equivalents required 3 months from component fabrication to fleet deployment. Admiral Shigeru Fukudome arrived at Yokosuka on May 22 to review the findings personally. Fukudome commanded the Second Fleet and was responsible for tactical doctrine in the Combined Fleet's war against American naval forces. He had built his career on the assumption that Japanese technological skill, combined with superior night-fighting tactics and the spiritual superiority of Japanese sailors, would overcome American material advantages. The captured radar threatened to invalidate every tactical assumption he had made. Watanabe's briefing lasted 4 hours. He walked Fukudome through each component, explaining not just what the Americans had achieved, but what it meant operationally. The Admiral, a battleship commander from the old school who still believed decisive fleet actions would be fought at visual range with big guns, struggled to grasp implications that Watanabe himself had barely absorbed. This device, Watanabe explained, holding up a component smaller than a pack of cigarettes, allows American ships to detect our vessels at ranges exceeding 30 kilometers. In darkness, in rain, in fog. Conditions that we have relied upon for tactical advantage now favor the enemy. He paused, letting that sink in before continuing. But detection alone is not the critical factor. This radar feeds directly into their gun directors. American ships can achieve firing solutions and engage targets they cannot see with their eyes. They can do this faster than our crews can load and train guns using optical rangefinders. Fukudome understood naval gunnery at a visceral level. He had served on battleships for 20 years, lived through the endless drills that perfected optical rangefinding and fire control. Japanese gun crews were the best in the world, capable of precision that Americans couldn't match. Except none of that mattered if American crews didn't need to match it. They had replaced human skill with electronic calculation, individual excellence with systematic advantage. The Admiral asked the question that had been forming since he entered the room. Can we produce equivalent devices? Can our laboratories match this capability? The silence that followed was answer enough, but Watanabe provided details anyway. Our magnetron production cannot increase significantly without retooling that would take years and require materials we do not possess. The vacuum tubes use tungsten and rare earth elements that must be imported. The precision machining requires tools we have in limited quantities. Our best estimate, assuming unlimited funding and highest priority, is that we could produce 20 radar sets per month within 1 year. We currently produce 4 sets monthly. He continued, his voice flat with the exhaustion of a man delivering a terminal diagnosis. The Americans, based on the production codes we have documented from this single unit and intelligence from other captured equipment, are manufacturing radar sets by the thousands each month. They are installing them not only on capital ships and cruisers, but on destroyers, destroyer escorts, patrol craft, and even merchant vessels. Within 6 months, every American ship in the Pacific will have radar capabilities superior to our most advanced units. Fukudome asked about countermeasures. Could Japanese ships detect when they were being tracked by radar? Could they jam the signals, spoof the returns, develop tactics to minimize exposure? Watanabe had anticipated these questions. The answers were uniformly discouraging. Radar warning receivers would require miniaturized electronics we cannot produce in quantity. Jamming requires understanding of enemy radar frequencies and characteristics, then generating interference signals of sufficient power. We lack both the intelligence on American radar frequencies and the transmitters to jam them effectively. As for tactical countermeasures, American radar is largely immune to the weather conditions and darkness we have exploited. There are no environmental factors we can use to our advantage. The briefing moved to operational implications. Watanabe had prepared a comprehensive analysis, drawing on his knowledge of both Japanese and American naval doctrine. The conclusions were devastating to every tactical assumption the Imperial Navy had made. Japanese night-fighting doctrine, perfected through decades of training and combat experience, assumed that darkness provided concealment and allowed skilled crews to close to torpedo range undetected. American radar eliminated this advantage entirely. Japanese ships approaching at night would be detected at maximum radar range, tracked continuously, and engaged with gunfire before they could establish firing positions for their superior long-lance torpedoes. Japanese surface raiders, fast destroyers and cruisers that had devastated Allied shipping in the war's early months depended on surprise and rapid engagement. American radar-equipped convoy escorts could detect raiders before visual contact, directing fighters or coordinating defensive maneuvers that negated Japanese speed advantages. The submarine threat, always minimal in the Imperial Navy's planning, became acute when considering that American point submarines were being equipped with surface search radar, allowing them to detect targets at night and in weather conditions that previously protected shipping. Most critically, the American advantage in radar fire control meant that Japanese ships would be hit before they could return effective fire. Gun battles that Japanese crews trained to fight at 10 to 15 kilometer ranges would now occur at 20 to 30 kilometers, ranges where optical rangefinders became increasingly inaccurate, while radar-directed fire remained precise. The mathematical advantage was overwhelming. If American ships could hit with 50% accuracy at 25 kilometers, while Japanese ships achieved only 20% accuracy at the same range, and if Americans could open fire when Japanese ships were still maneuvering into range, the outcome of any surface engagement was predetermined. Fukudome listened to this cascade of bad news with the stoicism expected of a flag officer. But Watanabe, watching carefully, saw the moment when understanding crystallized into horror. The Admiral's face remained composed, but his hands, clasped behind his back, betrayed tension that bordered on panic. Everything Fukudome had trained for, everything the Imperial Navy had perfected through brutal discipline and endless drilling, was obsolete. Not inferior. Obsolete. The Admiral asked for time to study the reports privately. Watanabe left him in the small office adjacent to the laboratory, surrounded by technical documents and operational assessments, a warrior confronting the mathematical proof of his own irrelevance. When Fukudome emerged 3 hours later, he had aged visibly. The confidence that characterized Japanese flag officers, born of decades of assumed superiority, had been replaced by something else. Not defeat, not yet, but the recognition that defeat was inevitable unless something fundamental changed. That evening, Watanabe joined a dinner with the technical team at a restaurant near the naval base. The conversation, lubricated by sake, turned philosophical. These were Japan's finest technical minds, men who had devoted their lives to keeping the Imperial Navy at the cutting edge of naval technology. They had believed, with good reason based on pre-war performance, that Japanese engineering could match or exceed any potential adversary. The captured American radar had shattered that belief with the brutal efficiency of empirical evidence. Lieutenant Nakajima, already well into his cups, voiced what others were thinking. "We have been building masterpieces while they have been building machines. We craft each radar set like a sword, perfect and unique. They stamp them out like bullets, crude but effective and innumerable. A master swordsman with a perfect blade cannot defeat 1,000 conscripts with rifles." The metaphor resonated because it captured the essential difference in philosophy, Japanese engineering culture. Inherited from centuries of XITRAs, craftsman tradition, emphasized perfection in individual pieces. The idea of deliberate over-engineering, building robust systems with generous tolerances that could be maintained by average technicians rather than specialists, seemed wasteful and imprecise. American mass production, with its acceptance of good enough standards and its focus on volume over individual excellence, had seemed philosophically inferior. The war was demonstrating that philosophy was subordinate to arithmetic. Watanabe shared something he had observed during his years in California, an anecdote that illuminated the cultural gulf. He had visited an American factory producing commercial radios, millions of units annually for civilian consumers. The production line moved with mechanical precision. Components were tested by machines, not craftsmen. Rejected units were discarded without ceremony, their parts recycled. The American engineer escorting him had explained their quality control philosophy: build-in, redundancy, design for replacement rather than repair, accept failure rates that would horrify Japanese manufacturers, then compensate with volume. At the time, Watanabe had found this approach almost offensive. Japanese craftsmen took pride in zero-defect production. The idea of accepting failure as inevitable and building systems to accommodate it seemed like surrender to mediocrity. Only later, studying American military production, had he understood the genius of the approach. When you produce millions of units, individual failures become statistical noise. When replacement parts are standardized and readily available, repair becomes trivial. When operators expect equipment to work without specialized training, you can deploy technology to forces that would never receive it under Japanese systems requiring expert operators. The Americans had democratized technology. They had made sophisticated equipment usable by ordinary people. The Japanese had kept technology, the province, specialists, which meant that their most advanced capabilities depended on small numbers of irreplaceable experts. In a war of attrition, which approach would prevail? The dinner party already knew the answer. The implications of the captured radar extended far beyond tactical disadvantages in surface combat. Over the following weeks, as analysis deepened and more intelligence arrived from field commanders, a comprehensive picture emerged of how completely radar had transformed naval warfare. Each new understanding brought fresh despair to officers who had spent careers mastering doctrines now rendered obsolete. Commander Toshikazu Omai, assigned to evaluate how American radar affected carrier operations, delivered his assessment in early June 1943. His findings were perhaps the most disturbing of all. Japanese carrier doctrine, refined through years of training and validated by stunning victories in the war's opening months, depended on launching massive coordinated strikes at maximum range. Japanese pilots were trained to navigate hundreds of kilometers over open ocean, locate enemy carriers, attack in overwhelming force, then return to their ships. This required exceptional skill, intensive training, and pilots of rare ability. Japanese naval aviation had produced such pilots through brutal selection and endless drilling. By mid-1943, most of those irreplaceable pilots were dead. American radar changed the fundamental calculus of carrier warfare. Ships equipped with air search radar could detect incoming strikes at ranges exceeding 150 kilometers, providing 30 minutes or more of warning. This allowed carriers to launch fighters, maneuver to avoid attack, and coordinate defensive fire in ways that negated Japanese numerical advantages. Japanese strike packages, trained to achieve surprise through skilled navigation and perfect timing, found themselves intercepted by fighter screens, directed by radar controllers who could see the entire tactical picture from a godlike perspective. The Americans had invented a new role, the fighter director officer, who sat before radar scopes and guided interceptors to their targets using radio communication. Japanese fighters, lacking airborne radar and operating under radio silence doctrine that emphasized pilot initiative over centralized control, couldn't match this systematic approach. American fighter direction turned aerial combat from a contest of individual skill into an orchestrated response, overwhelming Japanese pilots through coordinated tactics that radar made possible. Omei's report included intercepts of American radio communications from the Battle of the Philippine Sea, still months in the future, but foreshadowed by smaller engagements already demonstrating American radar superiority. The intercepts showed American carriers detecting Japanese strikes at such extreme ranges that they could launch multiple fighter waves, stacking their defenses in depth. Japanese pilots who survived the first interception faced fresh fighters on their second approach, then more fighters after their attack, then yet more during their retirement. The systematic destruction of Japanese air power wasn't primarily due to superior American aircraft or pilot skill, though both factors contributed. It was due to radar-directed defense that turned the sky into a killing ground where Japanese formations were tracked, intercepted, and destroyed with industrial efficiency. The submarine dimension of radar supremacy proved equally devastating. Japanese anti-submarine doctrine, never a priority in a navy focused on decisive fleet actions, was catastrophically inadequate against radar-equipped American submarines. Commander Atsushi Oi, one of the few Japanese officers who had advocated for comprehensive anti-submarine warfare, presented findings that illustrated the helplessness of Japanese merchant shipping against an enemy who could see in the dark. American submarines, equipped with surface search radar, could operate at night with impunity. They could detect merchant convoys at ranges where they themselves were invisible, maneuver into attack positions without being observed, and withdraw before dawn made them vulnerable to air search. Japanese escorts, lacking radar, depended on visual lookouts and sonar, both nearly useless at night or in poor weather. The result was a massacre of Japanese shipping that was strangling the empire's war economy. The mathematics were brutal. Japan needed to import 6 million tons of material annually to sustain its military operations and civilian economy. This required a merchant fleet of at least 4 million tons operating continuously. American submarines, guided by radar and supported by code breaking that revealed convoy routes, were sinking Japanese shipping faster than replacements could be built. By mid-1943, monthly losses exceeded 100,000 tons, while Japanese shipyards, lacking the steel and labor for expansion, produced fewer than 50,000 tons monthly. The trend line pointed to economic collapse within 2 years. Oi's presentation included a demonstration using a captured American submarine radar set recovered from a boat damaged and scuttled in shallow water. The device, mounted temporarily on a Japanese patrol vessel, detected a friendly merchant ship at 40 kilometers in complete darkness. The Japanese ship's lookouts, some of the best trained observers in any navy, saw nothing even when directed to the exact bearing. Radar operators tracked the target continuously, providing range, bearing, and speed with precision that optical rangefinders couldn't match in daylight. The demonstration lasted 20 minutes. Every officer present understood they had witnessed the technological foundation of Japan's impending starvation. Admiral Fukudome convened a conference in late June to assess whether any countermeasures could address the radar disadvantage. The gathering included every senior technical officer in the Imperial Navy, representatives from the Naval Technical Research Institute, liaison officers from frontline units, and civilian scientists from Japan's premier universities. The diversity of expertise made no difference. The conclusions were unanimous and devastating. Dr. Hidetsugu Yagi, whose research on directional antennas had pioneered radar development in the 1930s, gave the most authoritative and pessimistic assessment. Yagi's work on beam antennas, still called Yagi antennas by engineers worldwide, had given Japan an early lead in radar research. That lead had evaporated through lack of resources, competing military priorities, and most damaging of all, institutional resistance to new technology from naval officers who trusted their eyes more than electronic instruments. Yagi explained that Japanese radar research had focused on perfecting individual systems rather than mass deployment. The Imperial Navy operated perhaps 20 radar sets across its entire fleet. Intelligence suggested the American Navy had deployed thousands, with production accelerating monthly. The disparity wasn't due to Japanese technical incapability, but to fundamentally different approaches to technology integration. Americans accepted that radar would sometimes fail, that operators would make mistakes, that systems would require maintenance. They built redundancy and simplicity into their designs, accepting lower peak performance in exchange for reliability and ease of operation. Japanese engineers, by contrast, had pursued maximum performance from each radar set, creating complex systems that required constant adjustment and specialist operators. This approach made sense for laboratory research or limited deployment on capital ships. It failed catastrophically when trying to equip an entire fleet operating across millions of square kilometers of ocean. The Americans understood something Japanese technical culture resisted. Good enough, deployed widely, beats perfection deployed rarely. The conference participants grappled with whether Japan could shift to American-style mass production. The answer was unambiguously negative. Japanese industry lacked the machine tools, the standardized components, the electrical manufacturing capacity, and most critically, the raw materials. Radar sets required copper for windings, tungsten for vacuum tubes, quartz crystals for frequency control, specialized steel alloys for waveguides. Japan had limited domestic supplies of all these materials and increasingly tenuous supply lines to sources in occupied territories. Even if materials could be secured, retooling Japanese factories to produce thousands of radar sets would require years and divert resources from other critical needs. The Naval Technical Research Institute estimated that maximum feasible radar production, assuming unlimited funding and highest priority, might reach 100 units monthly by late 1944. By then, the Americans would be producing thousands monthly. The gap wouldn't close, it would widen. Lieutenant Commander Nakajima, whose enthusiasm for Japanese technical prowess had sustained him through years of difficult research, spoke with the flat effect of a man whose faith has been shattered. His laboratory had achieved genuine breakthroughs, developing centimetric radar that matched American performance in controlled tests. But converting laboratory prototypes into fieldable equipment had proven impossible. Each radar set required 200 hours of skilled labor to assemble and calibrate. Vacuum tubes, hand-selected and individually tested, had failure rates exceeding 20%. The complete systems, while functional, were so delicate that shipboard vibration and salt spray degraded performance within weeks. American radar sets, by contrast, were designed for abuse. Nakajima had examined the captured SC radar in excruciating detail. Every component was overbuilt. Vacuum tubes were socketed for replacement by technicians with minimal training. Critical adjustments were eliminated through circuits that self-compensated for temperature and voltage variations. The waveguides were thick enough to withstand rough handling. Cable connectors were waterproof and foolproof. The entire design philosophy prioritized operational reliability over theoretical performance. This difference in design philosophy reflected deeper cultural divides. Japanese engineering excellence focused on pushing theoretical limits, achieving maximum performance through perfectionist craftsmanship. American engineering, shaped by mass markets and continental distances, prioritized robust systems that worked consistently in hands of average users. Neither approach was inherently superior in all contexts, but for equipping a fleet fighting across the Pacific, the American approach was devastatingly effective. While Japanese perfectionism proved paralyzing, the conference concluded with recommendations that read like a surrender document. The Imperial Navy should prioritize radar production, But expectations must remain realistic. Maximum production would equip capital ships and fleet carriers, leaving destroyers, submarines, and merchant vessels without radar for the war's duration. Training programs should emphasize radar operation, but the specialized skills required meant only a fraction of ships would have competent operators. Research should continue into countermeasures like radar warning receivers and jamming equipment, but deployment timelines stretched into 1945 or beyond. Most damning was the operational recommendation. Japanese naval forces should avoid night engagements where radar advantages were most pronounced. This meant abandoning the night fighting doctrine that had been Japanese naval strategy's cornerstone. Decades of training, refined tactics, specialized equipment, all were rendered obsolete by an electronic device that let Americans see in darkness. Admiral Fukudome read the conference summary in his quarters aboard the battleship Musashi. Outside, the greatest warship ever built by Japanese industry floated in Truk Lagoon, a monument to the fleet-decisive battle doctrine that had governed Japanese naval planning for half a century. Musashi's 18-inch guns could destroy any ship afloat at ranges exceeding 40 kilometers. Her armor could withstand hits from the heaviest shells. Her construction had consumed resources equivalent to building 5 aircraft carriers. None of that mattered if American ships could hit her from beyond visual range, while her own guns, relying on optical rangefinders, struggled to find targets in darkness or weather. The Admiral understood, with the clarity that comes from facing undeniable evidence, that Japan had lost the technological war before the shooting war began. Not through lack of skill or intelligence or dedication. Japanese engineers and scientists were equals to any in the world. But engineering excellence without industrial capacity meant creating masterpieces that couldn't be reproduced in quantity. Japan had built an exquisite military machine optimized for short, decisive conflicts. The Americans had built a crude but unstoppable production system, optimized for attrition warfare. In his private journal, Fukudome wrote words that would have been treasonous if discovered. "We examined their radar and saw our defeat written in vacuum tubes and waveguides. They have made technology into a commodity, while we treat it as art. Artists cannot defeat factories. Craftsmen cannot overcome assembly lines. We fight with precision instruments against mass-produced weapons." The outcome was determined not by this battle or that, but by production statistics compiled in factories we cannot match. The captured American radar sat in its examination room at Yokosuka, disassembled across tables covered with detailed diagrams and measurements. Japanese engineers had learned everything they could from studying it. They understood its principles, admired its design, and recognized their inability to replicate it at scale. The device was a message from the future, and the message was defeat. Not eventual defeat or possible defeat, but mathematical certainty. The Americans had mastered mass production of sophisticated technology. Japan had not. In industrial warfare, that single difference determined everything. The revelations from the captured radar analysis spread through the Imperial Navy's command structure, like poison through veins. What began as technical assessment metastasized into strategic paralysis as officers at every level confronted implications that invalidated their training, their doctrine, and their understanding of naval warfare itself. The crisis wasn't merely technological, it was existential. Vice Admiral Takeo Kurita, commanding the 2nd Fleet's cruiser division, received Fukudome's report while his ships patrolled near Truk. Kurita had built his reputation as a night-fighting specialist, leading destroyer squadrons in the brutal surface actions around Guadalcanal, where Japanese torpedoes and superior optical equipment had devastated American task forces. Those victories, achieved at terrible cost against numerically superior forces, had seemed to validate decades of training in night combat. The radar report revealed those victories as temporary flukes, successes possible only because American radar deployment in late 1942 had been incomplete and poorly integrated into tactical doctrine. By mid-1943, American commanders had learned to leverage their radar advantage ruthlessly. They engaged at longer ranges, coordinated ship movements using radar plotting, and fired with accuracy that Japanese optical rangefinders couldn't match in any conditions less than perfect visibility. Kurita's cruisers, magnificent ships with superb crews, were being reduced to targets whose only hope for survival was avoiding detection entirely. The predator had become prey. Kurita gathered his captains for a sobering discussion of tactical options in the new radar-dominated environment. These were experienced combat commanders, veterans of multiple engagements, men who understood naval warfare at a visceral level. Their discussion revealed how completely radar had inverted their tactical understanding. Every conventional wisdom, every hard-won lesson, every tactical principle they had mastered now worked against them. Japanese doctrine emphasized aggressive engagement, closing to torpedo range where the superior long-lance weapons could devastate enemy formations. But closing range required stealth and surprise, which radar eliminated. American ships detected Japanese formations at such distances that they could maneuver away, maintaining ranges where their superior radar fire control gave overwhelming advantage. Japanese ships couldn't force close engagement against enemies who saw them coming from beyond the horizon. Captain Tamechi Hara, commanding the destroyer Shigure, contributed an observation that crystallized the tactical impossibility. We train our lookouts to near superhuman levels of visual acuity. Our best observers can detect ships at ranges approaching 30 kilometers in perfect conditions. But perfect conditions are rare. In darkness, in rain, in haze, our lookouts are blind while American radar sees clearly. We have optimized for rare conditions while they have eliminated dependence on conditions entirely. This observation prompted uncomfortable reflection on how much Japanese tactical advantage had relied on specific conditions, rather than general superiority. Night engagements favored Japanese crews only in clear weather with adequate moonlight. Heavy weather operations gave advantage to the side with better seamanship, but radar negated seamanship advantages by providing precise navigation and target tracking regardless of visibility. The tactical situations where Japanese training and equipment provided advantage were shrinking to vanishing insignificance. The discussion turned to whether Japanese forces could develop radar countermeasures that might restore tactical balance. The options were limited and discouraging. Radar warning receivers, which could alert ships when they were being tracked, required electronic components Japan couldn't produce in quantity. Even if warning receivers existed, what action could crews take? American radar ranges exceeded gun ranges. Being warned of detection didn't help if you couldn't escape or strike back effectively. Radar jamming seemed promising until technical officers explained the difficulties. Effective jamming required transmitters powerful enough to overwhelm enemy radar at considerable distances. This meant large equipment consuming substantial electrical power, challenging to install on warships already cramped and overloaded. Moreover, jamming revealed your position as clearly as a searchlight, inviting concentrated fire from multiple enemy ships. The mathematics of electronic warfare favored defenders with multiple receivers over attackers with single jammers. Chaff, the use of metal strips to create false radar returns, offered some potential, but chaff deployment was still experimental even in American and British navies. Japanese research into chaff had barely begun, and operational deployment was years away. Meanwhile, American radar technology was advancing rapidly. Intelligence reports suggested they were developing frequency-agile radars that could shift wavelengths to defeat jamming and confusion techniques that hadn't even been deployed yet. The tactical discussions revealed a deeper problem beyond any specific countermeasure. Japanese naval doctrine was built on decisive battle concepts inherited from Mahanian theory and validated by the Battle of Tsushima. Japanese officers trained to seek engagement, close with the enemy, and achieve victory through superior fighting spirit and tactical skill. But radar rewarded avoidance and standoff engagement. The side with better sensors could choose engagement ranges and decline battle when disadvantaged. American forces, with radar superiority, could implement Fabian tactics that Japanese doctrine had no answer for. Captain Hara voiced the unspoken conclusion: "We have trained for 40 years to fight a war that will not occur, the decisive fleet engagement, battleships pounding each other at visual range while destroyers press torpedo attacks through shellfire. This exists only in our planning documents. The Americans will never give us that battle. They will engage at ranges where their radar provides advantage and withdraw when we close. They will attrit our forces through standoff engagements we cannot win. We are samurai preparing for individual combat, while they assemble firing squads. This metaphor resonated precisely because it captured the mismatch between Japanese tactical culture and technological reality. Japanese naval training emphasized individual excellence, ship handling skill, tactical initiative by subordinate commanders. These were genuine strengths, products of intense training and careful selection, but radar enabled centralized coordination and systematic execution that overwhelmed individual excellence. American task forces, directed by commanders who could see the entire tactical picture on radar displays, executed coordinated maneuvers that Japanese forces couldn't match, despite superior seamanship of individual ships. The psychological impact of radar superiority extended beyond tactical disadvantage into something more corrosive, the loss of confidence that comes from fighting blind against opponents who see clearly. Japanese sailors, trained to believe their night vision and lookout skills were unmatched, discovered those skills were irrelevant. Lookouts strained their eyes into darkness while enemy ships, invisible to human vision, tracked them on radar scopes and prepared firing solutions. The experience was unnerving in ways that superior enemy firepower wasn't. Being outgunned was comprehensible. Being outseen felt like fighting ghosts. Commander Toshikazu Omei, continuing his analysis of radar's impact on carrier operations, discovered implications that extended beyond tactical engagements into strategic campaign planning. Radar had transformed carrier operations from episodic fleet engagements into continuous operations that ground down Japanese air power through attrition that couldn't be sustained. American carriers, with radar providing early warning of attacks and fighter direction, enabling efficient interception, could operate aggressively close to Japanese bases. They could launch strikes, recover aircraft, and defend against counterattacks with systematic efficiency that Japanese carriers couldn't match. Japanese carriers, lacking adequate radar, had to maintain greater distances from threats, limiting their strike ranges and effectiveness. The operational radius disparity meant American carriers could attack Japanese positions while remaining outside effective Japanese counterstrike range. More devastating was radar's impact on aircraft recovery. American carriers could recover aircraft at night and in weather conditions that grounded Japanese operations. Radar allowed controllers to guide damaged or lost aircraft back to the fleet, direct landing approaches in poor visibility, and coordinate complex operations involving multiple carrier launches and recoveries. Japanese carriers, dependent on visual signals and pilot navigation skill, could only recover aircraft in daylight and good weather. Pilots who couldn't find their carriers in darkness or clouds were lost, even if their aircraft were undamaged. The implications for campaign sustainability were stark. American carrier forces could maintain operational tempo regardless of conditions, launching strikes around the clock, recovering aircraft in any weather, sustaining operations that wore down Japanese air power through relentless pressure. Japanese carriers, constrained by daylight operations and weather limitations, operated episodically, ceding initiative to an enemy whose technological advantages enabled sustained operations. Omei calculated that American carrier task forces achieved approximately 70% operational availability, meaning they could conduct offensive operations on 7 days out of 10, with the remaining time used for logistics and maintenance. Japanese carriers, by contrast, managed perhaps 40% availability, with more than half their time consumed by positioning, waiting for favorable conditions, and recovering from operations. This availability disparity, multiplied across months of campaigning, meant American forces delivered 3 strikes for every 2 Japanese strikes, a cumulative advantage that was crushing Japanese naval aviation through mathematical inevitability. The economic dimension of radar superiority proved equally devastating. Japanese maritime commerce, the arterial system keeping the empire alive, was hemorrhaging under assault from radar-equipped American submarines. Each month brought fresh statistics that traced Japan's slow economic strangulation with numerical precision. August 1943 saw Japanese merchant losses exceed 150,000 tons. September brought another 140,000 tons lost. October added 160,000 tons to the butcher's bill. American submarines, guided by radar that let them operate effectively at night and in weather that had previously protected convoys, were sinking Japanese shipping at rates that exceeded construction by factors of 3 or 4. The mathematics were inexorable. Japan began the war with approximately 6 million tons of merchant shipping. Losses in the first year reduced this to 5 million tons. Current loss rates projected the merchant fleet would drop below 4 million tons by mid-1944, below 3 million by year's end. The economic minimum to sustain military operations and prevent civilian starvation was estimated at 4 million tons. The trend lines intersected at a point representing national collapse, and radar-equipped American submarines were the primary factor driving those trend lines toward catastrophe. Commander Atsushi Oi, whose anti-submarine warfare analyses had been consistently ignored in a navy focused on fleet actions, delivered updates that read like medical reports on a terminal patient. Japanese escort forces, expanded desperately in response to mounting losses, lacked the radar and sonar equipment to effectively counter American submarines. Japanese destroyers and escort vessels hunted blind, depending on visual, sightings in daylight and luck at night. American submarines hunted with radar that penetrated darkness and weather, attacked with impunity, and withdrew before escorts could respond. The few Japanese successes against American submarines came largely from chance encounters or American errors, not from effective anti-submarine doctrine. American submarine losses in the Pacific averaged 2 per month, unsustainable for any navy but manageable for American production that launched new submarines faster than losses occurred. Japanese merchant losses averaged 400,000 tons quarterly, completely unsustainable against construction capacity of perhaps 150,000 tons quarterly. Oi's reports included heartbreaking accounts from merchant captains who survived submarine attacks. Ships torpedoed at night never saw their attackers, never had opportunity to maneuver or fight back, simply exploded and sank while survivors wondered what had killed them. Escorts, arriving at attack sites, found wreckage and survivors but no submarines to counterattack. The Americans struck invisible and vanished unseen, leaving only bodies and burning oil to mark their passage. The strategic implications transcended military concerns into existential threat. Japan was an island empire utterly dependent on maritime commerce. The home islands produced almost no oil, limited food, insufficient raw materials for war production. Everything had to be imported from occupied territories, then distributed across the empire by sea. American submarines, leveraging radar to dominate night surface operations, were severing these vital connections with surgical precision. Oil shipments from the Dutch East Indies, essential for fleet operations and industrial production, were particularly vulnerable. Tankers were large, slow, and highly visible to radar. Submarine attacks on tanker convoys achieved hit rates exceeding 50% by late 1943. Multiple tankers per convoy were being sunk, making even successful convoys Pyrrhic victories that delivered less cargo than the voyage consumed in escort fuel. The combined fleet was increasingly immobilized by fuel shortages, despite controlling oil fields in Southeast Asia. The oil existed, but couldn't reach Japan. Food imports faced similar interdiction. Rice shipments from Southeast Asia, soybeans from Manchuria, fish from coastal waters, all moved by sea routes that American submarines controlled through radar-enabled night operations. Civilian rations in Japan were being reduced systematically as imports dried up. By late 1943, average caloric intake in Japanese cities had fallen 20% below pre-war levels. Projections suggested further reductions of 30 to 40% by mid-1944 if shipping losses continued. The empire faced not just military defeat, but mass starvation. Admiral Osamu Nagano, chief of the Naval General Staff, confronted these realities in a series of conferences during autumn 1943. Nagano had been one of the architects of the decision to go to war with America, convinced that early victories would secure a defensive perimeter that America couldn't penetrate without prohibitive losses. The radar revelations and mounting submarine toll revealed that assumption as catastrophically wrong. America wasn't trying to penetrate the perimeter. They were strangling Japan from outside it through technological advantages that Japanese forces couldn't counter. Nagano's staff presented options that ranged from inadequate to fantastical. Increase escort production, but this required steel and labor already committed to combatant construction. Develop radar and sonar, but this required years and materials Japan lacked. Route shipping closer to coast where air cover might protect convoys, but this added thousands of kilometers to voyages and reduced total cargo throughput. Institute convoy systems modeled Allied practice, but Japan lacked escort vessels in sufficient numbers for effective convoy defense. Every option required resources that didn't exist or time Japan didn't have. The staff discussions revealed deep fractures in Japanese strategic thinking. Army representatives insisted that resource imports were Navy responsibility and criticized naval failures to protect shipping. Navy officers countered that the Army's insistence on garrisoning every occupied territory dispersed naval forces too widely for effective concentration. Both services competed for limited resources, neither willing to accept reduced priority for their preferred strategies. The inter-service rivalry that had plagued Japanese planning throughout the war intensified as resources contracted and options narrowed. Underlying the strategic debates was a question that few wanted to voice, but everyone understood. Could Japan still win the war? The answer, based on every statistical measure and technical assessment, it was negative. Japan was losing the production war, the technology war, the attrition war, the economic war. American industrial output was accelerating while Japanese production stagnated or declined. American technical advantages in radar, sonar, proximity fuses, and code breaking were widening rather than narrowing. American replacement rates for losses exceeded Japanese rates by factors of 5 to 10 across every category of ship and aircraft. The economic strangulation from submarine interdiction was inexorable and accelerating. Yet surrender was culturally unthinkable, politically impossible, and institutionally inconceivable. Japanese military culture, shaped by Bushido traditions and reinforced by decades of indoctrination, regarded surrender as ultimate dishonor. The political structure offered no mechanism for negotiated peace. The institutional momentum of military operations, the careers and identities of hundreds of thousands of officers and men, all depended on continuing the war regardless of prospects for victory. Japan would fight on because the alternative was psychologically and culturally impossible, even as every objective measure indicated such continuation was suicidal. The captured American radar, still sitting disassembled in Yokosuka's research facility, represented more than a technological artifact. It was a message that Japanese leadership had been forced to read but remained unable to act upon. The message was clear. American industrial and technological superiority had made Japanese victory impossible and Japanese defeat inevitable. The only variable was time, how long Japan would continue fighting and how many would die before accepting the predetermined outcome. In the months following the radar analysis, Japanese naval operations took on a desperate quality. Commanders understood they fought not for victory but for time, seeking to inflict enough casualties that America might accept negotiated peace rather than demanding unconditional surrender. This hope was as delusional as earlier assumptions about technological parity, but it was the only hope available. The alternative was accepting that Japan's war was lost, and every subsequent death was meaningless sacrifice. The radar that had revealed these truths sat in its laboratory, surrounded by measurements and diagrams that told a story no one in power wanted to hear. Japanese engineers had learned everything they could from studying it. They understood the principles, admired the engineering, and recognized their inability to replicate it at scale. The device was a window into American capabilities that made devastatingly clear why Japan couldn't win a war of production and technology. Some truths, even when undeniable, remain unacceptable. The radar revealed such a truth. and Japanese leadership chose to ignore it, continuing a war they had lost before they began it, fighting on toward defeat that mathematics had already determined. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.